All right, guys, so this is Ms. Murphy, and I am going to be doing the second part of your 1.4 notes. So we finished up page 14, so I'm going to do a couple examples on page 15, and then we'll do some stuff about rotational symmetry. So when you are dealing with rotations, don't forget about those rules that we discussed in class today. So, for example, with this one, we're just going to do going clockwise now. So, we already discussed that counterclockwise is that if you start with xy, it would be negative y x for 90 degrees. It would be xy would now become negative x, negative y for 180 degrees. And then y, negative x for 270 degrees. So remember what I said, that basically all you got to remember or visualize if you're trying to figure out the um, the rules. All you got to visualize is if you're going from quadrant to quadrant, you're going to automatically switch the x and the y, and then you're going to change the signs to fit the quadrant. So every 90 degrees, you switch x and y, change the signs to fit the quadrant. That's how I remember it. Now, for clockwise, all right, so we're rotating 90 degrees clockwise. So here's our original figure right here. So this is at the point, I'm just going to go ahead and label the points. So this is at negative 2, 0, negative 3, 2, negative 4, 0, and negative 3, negative 2. All right, so we are now going to rotate this 90 degrees clockwise. So we're going in this direction. So I'm first going to look at what quadrant these are already in. So, for example, negative 3, 2. Okay. It's in quadrant 2, and I'm going to quadrant 1. So if quadrant 2 has to have points that are negative and positive, quadrant 1 has to have points that are positive, positive. So we start by flipping the x and the y. So it'll be some form of 2, 3. And then we make it so that it fits the quadrant, which it would stay positive. So this first point is going to be at 2, 3. Now, for the points that are on the x-axis, if we rotate them 90 degrees, they're going to end up on the y-axis, specifically the ones that are positive. So notice if you rotate this 90 degrees, both of these points 90 degrees, they're going to end up somewhere right here on the positive part of the y-axis. So I'm going to switch the x's and the y's. So just for reference, this is 2, 3. So I'm going to switch the x's and the y's for both of these. So 0 and then some form of 4. And since I know I'm going to have to go on the positive because this one's splitting 2 and 3, which means 90 degrees, it'll be splitting 1 and 2 quadrant. So it would be positive 2, 0, or 0, 2, my bad. And then positive 0, 4. Those would be my two new points. Now, my last point is right here in quadrant 3. So quadrant 3 is negative, negative. And just for reference, quadrant 4 is positive, negative. Now, since it's in quadrant 3 and I'm going 90 degrees clockwise, that means I'm going to end up in quadrant 2. So you start by flipping the signs, or not flipping the signs, sorry, flipping the numbers. So we're doing some form of 2, 3. And then in quadrant 2, the x value has to be negative. So this now becomes -2, +3. So it would be right here. This would be -2, +3. So our image will look something like this. So that one is going 90 degrees clockwise. Now, and it's asking us to plot out the points. So I'm just going to rewrite basically what I wrote up top. So the original points were -3, 2, -2, 0, 3, 2, and then -4, 0. So my new points after the first 90 degrees would be 2, 3, 0, 2, oh, this is both negative. Bad. So then that would be -2, +3, and then 0, 4. So what happened from xy to 90 degrees was that the x and the y flipped, and then the x became negative. All right, so technically the spot in the y place became negative. Because if you look at the points from here to here, our old x value is now positive when it was negative. Our old x value here is now positive. Our old x value here is now positive. Same thing here. So the signs flipped. Now, after 180 degrees, so just to save ourselves some time, we're going to go based off of our 90 degrees. So if we're rotating 180 degrees, that means I'm starting with what's on my new image. So, like I said, figure out what quadrant it's going to, and then you're going to flip them. So flip X and Y, and then change the signs to fit the quadrant. So for example, the point 2, 3 is in quadrant 1, meaning if we're going clockwise, another 90 degrees, which would give us to 180, this would go into quadrant 4, meaning that once we flip our X and Y, we need a positive X value and a negative Y value. So if it's the point 2, 3, this now becomes the point 3, -2, which I'm also going to write down here. So this now becomes 3, -2. Now, these two points that are on my y-axis, if I go another 90 degrees, they're going to land on my x-axis. So I'm going to flip the x and y again, and since they're on the positive x-axis, they're going to remain positive. So these two are both going to end up on the x-axis. So this would then be 2, 0, and 4, 0. And then lastly, -2, -3. It's in quadrant 2, so 90 degrees away to make a full 180. It will be in quadrant 1, meaning we're going to flip the x and the y, so it will be 3 and 2 of some sort. And since quadrant 1, both points or both parts of the coordinate have to be positive, that means this will remain as 3, 2. So right here. So our new shape would look like this. And then I'm just going to label the points quickly. So 3, 2, 4, 0, 3, negative 2, and 2, 0. I'm also going to take a minute, label them down here. So this is 2, 0, 3, 2, and 4, 0. So that means what happened with the rule is that the x and y came back to where they're supposed to be. But now if you look between the original point and after 180, the signs completely flipped. So that means they both changed signs. We're going to put a negative in front of them. Lastly, 270. So we're going to go off of our 180 and rotate it another 90 degrees clockwise. So same process all over again. So we're going another 90 degrees. So I'm going from 3, negative 2, 90 degrees away. We'll end up in quadrant 3. So I'm going to have to flip the x and the y. So I'm going to end up with 2 and 3 of some sort. And since it's going in quadrant 3, both of these have to be negative. So my new point for 3, negative 2 would be negative 2, negative 3. So right here. So negative 2, negative 3. Then these two that are on the x-axis, 90 degrees, they'll end up on the y-axis here, but in the negatives. So that means we still switch the x and y, so that'll be 0, negative 2, and 0, negative 4. So they started here and they ended up here. And then finally, 3, 2, it's going to start in the first quadrant, and it's going to end up in the fourth. So that means we flip the x and y, so it'll be 2, 3 of some sort, and since quadrant 4 has to be positive and then negative, it'll become 2, negative 3. So our figure will look like this. So this would be 0, negative 2, 2, negative 3, 0, negative 4, and negative 2, negative 3. And I'm going to label them as such down here. So 0, negative 2, negative 2, or not negative, positive 2, positive 2, negative 3, and then 0, negative 4. So if we looked at the points compared to the original, so in the green, what happened is that the x and y switched, but then the y value became negative. So if we write this rule, that means if we're going clockwise 90 degrees, that means we're going from y, negative x, which if you think about it, it means we're going from the first quadrant to the fourth quadrant. So that's a way to think about it. If we're talking about positive points, that means first quadrant to fourth quadrant, because that's where it is clockwise. However, like I said, you just look at the quadrant that you're starting in, flip x and y every 90 degrees, change your point values to fit the sign, to fit the quadrant. So change your signs to fit the quadrant. So 180 will be exactly like it is for counterclockwise. So negative x to negative y. And then 270 will be from negative y to x. And remember, this is backwards. So if we want to go counterclockwise, so for number 6, 90 degrees clockwise is equivalent to 270 degrees counterclockwise. 180 is just equivalent to 180 in either direction. And 270 is 90 degrees counterclockwise. So again, if you have trouble remembering the rules, all you need to remember is to switch X and Y every 90 degrees, regardless of which direction you're going. And then flip the signs to fit the quadrant. So whatever type of points you're supposed to have in that quadrant, that's what you change your signs to. All right, so the rest of this I want to give you for homework. So page, I believe this is 16. So the rest of page 16 is part of your homework. And just one more note that you need. Another way to write a rotation is with a big R, and then it'll tell you 90 degrees, like how you want to write it. So whether it's clockwise, counterclockwise, whatever. All right. Now that we've talked about the rotations, let's get into something that goes along with rotations as well as with reflection, which is symmetry. So as you know, symmetry means that if you fold it in half, it makes two congruent pieces. So with rigid transformations, there is some ways that you can have nice symmetry. So it's the ability to map an image onto itself shows that a figure has symmetry. So we are going to discuss the two types of symmetry that the shape can have, which is a line of symmetry and rotational symmetry. Now, if we're talking about a line of symmetry, that means the figure can be mapped onto itself by a reflection. So maximum lines of symmetry that a shape can have is that a polygon can have equal to its number of sides, and the maximum is always found in a regular polygon because all the sides, all the angles are congruent. So for example, if we look at the two shapes below, the octagon right here has 8 lines of symmetry max because it's a regular octagon, meaning all the sides are congruent, and they show all the 8 lines here. The pentagon has 5 max lines of symmetry because it has 5 congruent sides. Oops. Now, it's now asking what line could we reflect triangle ABC with the vertices A, so basically these 2 points, so that it maps onto itself. We're going to draw that line on the graph. So I am going to graph these points first. So A is -1, 3. B is 3, 6. And C is 7, 3. So what this means is that if we picked a line of symmetry so that it will flip onto itself, it just means that regardless of where we move it, it'll still remain in this exact same spot. So this is ABC. So what that means is that we essentially want to cut the shape into equal pieces in half. That's where our line of symmetry want to be. Because when we look up at the top, if I take one of these lines of symmetry for the octagon, it would cut it in half perfectly. Same thing for the pentagon. It would cut it in half perfectly. So that's what we need to find. Now, just by looking at it, we can figure out that right here, going through point B would perfectly cut our shape in half. So this would be the line x equals 3. And then we can check it. So if we do the equal distance thing, well, B prime will remain where B is because it's on the line of reflection. C is 1, 2, 3, 4 away. So it's 1, 2, 3, 4 away on the other side. So it's now where A is. What in the... So it's now where A is. So that's C prime. And then A, same thing. It's 4 away. So they would now be on where C is. So that's what it means when it maps onto itself. It remains in the exact same spot. So that line would be at x equals 3. Now, we can then just see if it has a line of symmetry or not. All right. So our first one here is a square. So it has a couple of lines of symmetry because we can definitely cut a square into equal pieces. So here, here, as well as its diagonals. All right. So yes, it has a line of symmetry. And it has 4 lines of symmetry. Because remember, if we're talking about a regular polygon, a square is a regular version of a rectangle. Since it has 4 sides, that means there are 4 lines of symmetry. Now, next is the parallelogram. Now, this one is a little tough, so we can test some of them, but it doesn't look like, well, there might be. So, first off, if we just test going straight down, all right, that's obviously not going to give us any kinds of symmetry there, so that's out. If we kind of go at an angle, so in other words, the line that we cut through is parallel to these 2 lines. So this line is parallel to these 2 lines. That can definitely be a line of symmetry because if we mapped it or flipped it over, well, actually, no, that's a lie. Even though it looks like it cuts it evenly in half, it's not quite. Actually, no, yes, it is. Okay, sorry, guys, I'm totally being confusing. But this line right here, it's a transversal. It's also a parallel line. So if we think about parallel line properties, that means that this angle would be congruent to this angle because it's corresponding. Same thing here. This angle will be congruent to that angle. Because again, corresponding. All right, so since these will all be congruent in some way, that is a line of symmetry. So the other line of symmetry would if we drew a parallel line congruent to the top parallels. Because same concept, they will reflect, and because of the parallel line properties cut by transversal, it works. But we can only use those lines of reflection if they are parallel to 2 of the sides. So this one only has 2 lines of reflection. Now this one's a bit tricky. So if you eyeball it, it looks like it might, but it really does not look like it has one. Because for example, if we cut it like this would be right here now instead of over here. Same thing here. This point would be here if we cut it that way. If we try horizontally, same problem. This point would be here and vice versa. Diagonally, Diagonally, it's also about the same. If we were to flip it, it would still not flip over correctly. So I'm going to say that this one does not have a line of symmetry. So no line of symmetry. Now, this one looks like it has a rotation of symmetry, though. So it may not have a line of symmetry, but it has a rotation of symmetry. And that's what we go into next. So, rotational symmetry, this is the type of symmetry that deals with rotation. So, what we just talked about. So, a figure has rotational symmetry if there is a center point about which the figure is rotated a number of degrees between 0 and 360, such that the image is congruent to the pre-image. All right. And then we excluded angles 0 and 360 because nothing happens in that case. It literally doesn't move or moves all the way around to the point it starts. It's at starting point. Now, the point around which you rotate, this is what we call the center of rotation. So, if we're on a coordinate grid, typically that center of rotation for us is the origin. It could be other places, but in this class, typically it will be at the origin. Now, the smallest angle you need to turn is called the angle of rotation. So, in order for it to be fully mapped on itself, that's how it would look again. All right. So, the figure has rotational symmetry of 72 degrees. So, this star has a rotational symmetry of 72 degrees. The center of rotation is the center of the figure. So, let's think about this. So, why 72? So, we're saying that if this is where we're rotating and we start here, if we rotate clockwise, or if we go backwards from this point to here counterclockwise, it will still be the same picture. Now, for a regular polygon with n sides, this polygon can be mapped back onto itself by a rotation of x degrees. So where x is 360 degrees divided by n. So if you think back up here, the 72, well, think about it. If we were to draw a circle around this star, a circle is 360 degrees. Well, we know that the tips of the star are where we want to land for the star to still look like the star that we started with. So if we do 360 divided by 5, all right, we should get 72 degrees, which if you put that in your calculator, that's exactly what you get. So that's why it's 72, because there's 5 places where it could be mapped onto itself as you rotate around. So that's also where this comes from, the x equals 360 over n, because if it's a regular polygon, meaning all the sides are congruent, it can map on itself at x degrees as long as we divide it by the number of sides that we have. Now, the order of rotational symmetry. So, order of symmetry is the number of times the figure coincides with itself as it rotates 360 degrees. So, for example, the order of symmetry up here for the star is 5. Because if we rotated it either direction, all the way around, there's 5 points that it has to hit in order for it to be the same picture and it's mapped onto itself. Now, what rotation would map a regular pentagon onto itself? What would the order of symmetry be for a regular pentagon? So, if we have a regular pentagon, and this is not going to be to scale, but it looks something like this, what would be the order of symmetry and what degree would we need here? So, again, imagine it's in the circle. All right, and that's a terrible circle. Let's do this. All right. It needs to hit 1, 2, 3, 4, 5 times. So the order of symmetry here is equal to 5, just like with the star. So that means if we did 360 divided by 72, not 72, divided by 5, our degree of rotation would be 72 degrees for that pentagon. All right. Now I'm going to leave these for you guys to try because it's a you try. So if you have questions about this, feel free to ask me on Tuesday. All right. So I'm going to leave these for you to try on your own, see how well you guys do. All right. And then the rest of the pages, so pages 19 and 20, those are also for homework for you guys. All right. If you have any questions, please feel free to email me, or you can save them for Tuesday and I will be happy to answer them. All right. And that's it for this video.